Hi everyone, this will be your video for continuity using calculus. So again, this will be on a calculus level. We'll be using limits to determine continuity. Okay, so here we are, and we're at our very first definition of the section, and we're talking about continuity at a specific point, at a specific c value. Just like how we can find limits at a specific c value, now we can talk about continuity at a specific value. So the following three statements that I'm going to be writing, they need to be shown for each and every problem. And that's how we can truly 100% say that yes, a function is continuous, or no, it is not. So the first condition that must be met is that f of c is defined. Okay, so what that means to us is that you can plug c in and you get a value out. So what I'll do is, in a different color, I'll write what we do for this step. We're going to evaluate f of x for c. Okay, we're going to plug it in. We're going to see what we get out. Now our next step has to do with our limit. Okay, so we need to make sure that our limit as x approaches c of f of x exists. Okay, so the way that we do that is we find our one-sided limit, and we need to make sure that both of our one-sided limits are equal to each other, which means that our limit does truly exist. So find one-sided limits, and they must be equal. Ran out of space there a little bit, but they must be equal for this limit to exist. So now we have our third condition that needs to be met. And this condition is more of like, like a conclusion step here. We need to evaluate what we've seen so far, and we need to figure out if this means that it's continuous or not. So our conclusion step here is that if we can find our limit, so if we find our limit as x approaches c of f of x, it must equal the function value. So whatever your condition was from step one. So that's really the idea here, is that after you find your information for step one, and then you find your information for step two, they must be equal. So number one and number two must be equal. Okay, so here we go. Again, we have to make sure our function is defined at that value. So plug in your c for x, solve. The second thing is that the limit must exist at x approaches c. And the third thing is that for it to be continuous, whatever you get from step one and whatever you get from step two must be equal to each other. So sometimes, either looking at a graph or going through the steps from our last slide, we do end up with a function that is discontinuous. And there are two different ways that we can have a discontinuity, two different types of discontinuities. So the first one that we have is what's called a removable discontinuity. Okay, so a removable discontinuity, it's called that because if f can be made continuous by just defining one specific point, so by defining f of c, okay? So basically this is like a point discontinuity. Okay, so one specific point is missing. So if we could replace one point back in, that's what's called a removable discontinuity. Now our other type of discontinuity has a very unique name. It's called non-removable. Okay, so now we have a non-removable discontinuity. Okay, and what that means to us, that's basically saying if our one-sided limits are not equal, or that they are unequal. Okay, so visually I'm going to just draw you a little graph here. It's not accurate at all, so don't really quote me on this. But so we have our first graph. A removable discontinuity could just be one point that's missing. So no matter what our graph is doing, it could be a line, it could be anything crazy. We'll just say it's like something like this. Maybe I get to a point where I don't have that point there, I have an open circle, and then it continues on. Okay, so our big issue with something like this is that if we were traveling along, we get to this point, There's nothing here. There's a hole in the graph. So we are going to figure out a way to determine if a function has this. But again, we can see this from a graph that one point put back in, and then we would be nice and smooth and continuous. So this is removable because it's one point that is missing. Now, on the other hand, a non-removable discontinuity, something that you might see might either be like a vertical asymptote or maybe a piecewise function just where the pieces aren't connecting. So I'll draw you both of them. And then we'll talk about how we can find this on our own. So for instance, one that's maybe a piecewise function, maybe we have a piece that comes to here, and then our next piece starts down here. Okay, so that's a big issue for us. We would need so many points to be able to link these sides together. Up here, with our removable, we only needed 1 point. Down here, with our piecewise, our non-removable discontinuity, we would need too many points to make this work. So this is a non-removable. And one other option might be an asymptote, like a vertical asymptote. So maybe we have something that looks like a rational function. And you can see that, again, there's too much space between these two sides. There's not just one point that can connect them. They're infinitely away from each other. So this is, again, a non-removable discontinuity when you have a vertical asymptote. So just to write that out, this is a vertical asymptote. And over here we have something like a piecewise function, or maybe if you see a jump discontinuity. Okay, so our first set of questions, our first set of examples here, we're given a graph. They're just asking us to find a little bit of information, find the limit from the left, the limit from the right, and if that limit exists, and then we can discuss the continuity. So you're going to see these directions a lot that say to discuss the continuity. Now, I don't expect you to go to Wawa and have a conversation with somebody about continuity, but when we talk about discuss, it's basically putting your information and your thoughts into words. So let's look at this first one. I know this is number 3, but just go with me on this first one. So the first thing we need to figure out is our limit from the right. So we have our limit as x approaches 3, because it's our c value right here, of this function f of x from the right. So as I'm coming in from the right, I'm following my graph, and I end up at my x value of 3, and my y value, where my finger would end up, is at 0. So my limit from the right is 0. Now we need to find our limit from the left, so the limit as x approaches 3 from the left of f of x. Okay, we're going to do the same thing. We can come through, we can follow along, we come all the way, and we end up at the x value of 3, y value of 0. So again, we have 0. So that means if both of those are equal, that our function, its limit as x approaches 3, we don't need any sort of direction onto that, of f of x also equals 0, because these are the same. So far that's good. We do have a limit. Now we also have a point, right? And we talked about that whole idea of continuity is that we have to have a point and we have to have a limit, and they need to be the same. So if we look at our point here, our function value, or what we could call f of c equals 1, because that's really like f of 3. That's our c value. So for this to be continuous, our function value and our limit must be the same. Okay, so let's keep that in mind. So I'm going to write a little note down here again, just to remind ourselves to be continuous. The limit as x approaches c of f of x must equal the function value when you plug in c. And for us, we can clearly see, if we wanted to discuss this continuity, this is going to be discontinuous. And it's discontinuous because f of c does not equal the limit as x approaches c. So you always want to explain why it is not continuous. So ours is not continuous because f of c does not equal the limit at c. So this we could also classify as a removable discontinuity. So this is removable. So you always want to give as much information as you can tell from this. You want to say, is it continuous? If it's not, what kind of discontinuity? And why is it not continuous? You want to make sure that you're getting your information across so that there's no room for error in answering your questions here. So let me just put a little box around that because that is part of my answer there too. Okay, let's look at our second little problem here. I'm going to erase some of this so we have a little bit more space. Okay, and for our second problem over here, let's see. All right, so now we're concerned with the x value of 2. Excuse me, negative 2. So the first thing I need to do is to find my limit from the left. Limit as x approaches negative 2 from the left of my function. And again, I can come through my graph, end up at the x value of negative 2. And my y value is also negative 2, so that's fun. And then I'm going to do the same thing, but now from the right of f of x. And we're looking and we say, okay, as we're coming in from the right, I might have to travel a little bit, and then I end up at negative 2 at my x's, and my y value is also negative 2. So lots of negative 2's here. Now the best part is these are equal, which is what we want, right? So when they're equal, that means that that's what the limit equals. So the limit as x approaches negative 2 equals negative 2. So that's a lot of information that we need. The only other piece of information we need to determine and to truly say that this is continuous is to find f of c. So f of c equals what? So for us, f of negative 2 is the value we're looking for. We find that point is filled in at negative 2, so equals negative 2. And I'm loving what I'm seeing here, even though it's a lot of negative 2's, but that's good, okay? We want them to be the same. So we can write our conclusion statement for our answer here. We can say that f of x is continuous. There we go. So f of x is continuous because f of c equals the limit as x approaches c of f of x. So sometimes you might have directions that say, let's discuss continuity, and we really need to think about what do we need to consider here. So obviously the first and foremost thing is it continuous? So if you have a graph or if you have better knowledge and you can just first off say it's continuous or not, there you go. If it's not continuous, you need to explain why it's not continuous. Just telling me that it's discontinuous is not going to give you full credit for an answer. You need to tell me why. If you find the domain, any restrictions in the domain, those are going to be values that are not in your, obviously, domain. And those are the reasons that you would not be continuous. So finding those restrictions, that will help. And also finding and listing any point discontinuities or vertical asymptotes. That's going to help you figure these out nice and swiftly. So looking at our examples over here, starting off, we have a polynomial function. Now, at this point, we can all understand that polynomial functions, like something that looks like this, is going to just be a parabola. It's going to be continuous. There's nothing going to be restricted in our domain, so we can say this is continuous. And then in parentheses, I'm just going to put it's a polynomial function. Okay, moving on. So now for our next one, we have 3x minus cosine of x. It's very helpful to understand the graph of cosine, and then even 3x minus cosine of x. You could plug that into Desmos, maybe look at the graph. Thinking about what you can plug into cosine, you can plug anything in, right? So our x values here are not restricted, so again, this is continuous. And one of the reasons for this one, if you'd like to give a reason, is the domain is all real numbers. So now we move on to the last one on this page, and this one has a whole different story going on here. The first thing I want to try to do is see if I can factor anything out. So when I factor out from my denominator, I'm left with x minus 1 times x. And notice that x is going to cancel out. So because it canceled out, now that's going to be a point discontinuity. So what we can do with the factor that did cancel out, which for us was x, we can take that factor and we're going to set it equal to 0. Generally, if we have more things that we need to do, you would solve here and you would solve for x. X is already solved for us. So at x equals 0, we're going to have a point discontinuity. It's such a long word. Okay, there we go. So we have a point discontinuity because that is the factor that canceled out. And then we also have to deal with what's going on down here, right? So we also have x minus 1 as our denominator. We're going to set that equal to 0. And what that's going to help us find is if we have a vertical asymptote. So we're going to solve. We get x equals 1. We're going to have a vertical asymptote at 1. At x equals 1. So we have point discontinuity at x equals 0. So what we can say is this. We definitely know that this is not continuous, right? That's our function there. So our final answer is discontinuous. We have a hole at x equals 0 and a vertical asymptote at x equals 1. And that would be a fantastic answer for that. So again, you can see these are just some other examples of functions that will have discontinuities. For instance, our first one right here, if we factor our denominator, we can think about factors of 10 that are going to combine to -3. So we're going to end up with x minus 5 times x plus 2. And you can see that that x plus 2 cancels out, and you're left with 1 over x minus 5. X plus 2 we set equal to 0. Oops. -2, that's going to be a point discontinuity. And then if we also take our x minus 5 and set that equal to 0, we're going to zoom in a little bit. So at x equals 5, we're going to have a vertical asymptote VA. So again, this helps us determine that this is not continuous. So discontinuous, oops, forgot the C. We have a hole at x equals -2, and we have a vertical asymptote at x equals 5. And that could be a nice little final answer there. So I'm not going to do the other ones on this page, but you can just see that you're going to either have ways that you can factor or you can work with these equations to find what values will not work. So one other way that we can talk about continuity is most specifically at a point. So this question right here is going to ask, is f of x continuous at 2? Okay, so this is obviously a piecewise function. I have a piece for when x is less than 2 and then a piece for when x is greater than 2. So my goal is to hopefully find out that I can plug in 2, I can find a limit at 2, and they're going to be equal. So our step 1 is to find f of 2. Okay, you're going to need some knowledge for your piecewise functions here. You need to determine which piece to plug it into because you're going to get different values. So if I plug it into the one where it says x is less than or equal to 2, this is the piece I'm going to be using. For any value greater than 2, it could be 2.01, I would be using this second piece down here because that's for values greater than 2. My top piece is for values less than 2 or equal. So we are plugging in 2, so we're going to be using our first function up, or the first piece of our function up top. So we're going to find f of 2, that means we're going to plug it in. We're going to have 2 times 2 minus 3, which is 4 minus 3, which is 1. So f of 2 is 1. Our second step, we need to find the limit as x approaches 2 of f of x. So the big deal is we need to figure out our limit from the left, which is going to be this one right here, because those are the x values to the left of 2. And then our limit from the right is going to be the second piece, because those are my x values greater than 2, so the values to the right of 2. So the first thing that we're going to find is a limit as x approaches 2 from the left, and that means that we're using the function on the top piece. So 2x minus 3, we can plug in that 2, so we get 2 times 2 minus 3, 4 minus 3, we get 1. Now we find our limit from the right. So limit as x approaches 2 from the right. We hope that this is going to be equal, so we're going to have x squared as our function here. And when we plug that in, we get 2 squared, which is 4. And this is a little heartbreaking, right? Because these values are not the same. So the limit from the left was 1. The limit from the right was 4. Those are clearly not the same numbers. So that means that this limit does not exist. Okay, so we can write that out in a little conclusion statement. Okay, so the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Then we can use this notation, which is just shorthand for the word therefore. The limit as x approaches 2 of f of x does not exist. Ran out of space there, so DNA. So these dots just mean therefore. So if you haven't seen them before, it's just shorthand like for your notebook or for work here. It's kind of like letting you come to a nice, educated conclusion. So our real goal is, after we do these first 2 steps, we will combine them, or not combine them, but we compare them, right? So step 3 is always, we need to hope that f of 2 equals the limit as x approaches 2 of f of x. And that's what we want, but for us, it is not equal. We have a big problem here because this limit does not exist, right? So if something doesn't exist, it can't equal 1, right? That's just pretty basic right there. So since that does not happen, this is discontinuous at x equals 2. So we're always following the same steps. First, we find the function value, then we find the limit, and then we hope that they're equal. If they are, that means that it is continuous. If they're not equal, that means that it's discontinuous, just for instance, like our problem here. Okay, and now our last example for continuity. So this is a whole different story now. They're saying that we want to figure out what value of a will make this continuous, right? We don't know for certain if this function's continuous yet. We need to figure out what value that we need to plug in for a into this little equation to make this work. So think about what it means to be continuous. For something to be continuous, again, you need to have that function value. The second thing we need to do, we need to have the limit as x approaches 1 of f of x. We need it to exist. Okay, so for it to exist, think about what that means. That means that the limit from the left of f of x has to equal the limit from the right of f of x. Okay, so we really need to evaluate and think about what we know as we're trying to solve these new types of problems. So for this limit to exist, from the left and from the right must be equal, right? So that means if I take my function, this is the left side, because those are values less than 1, and this is the right. Those are values greater than 1, and we want them to be equal when x is 1. So it's as simple as taking 7x minus 2 equals ax squared, and we want this to be equal when x equals 1. That's our value that we're looking at. Okay, we're trying to make this continuous at that crossover. So we're going to plug in 1 for all my x's. So plug in 1 for x's. All right, so that's our next step here. Let's do it. So we're going to have 7 times 1 minus 2 equals a times 1 squared. And we're going to just solve for a. And once we find it, that is our answer to this question. Remember, this question is only asking what value of a will make this function continuous. Okay? So think about what your questions are asking you. So now we have 7 minus 2 equals a times 1. And we have 5 to equal a. So we found out that once we plug in the 1 for our x's, we're going to solve for a. And once you find it, that is the value that if we made this function 5x squared instead of that ax squared, it would be continuous at 1. So again, remember that for it to be continuous, the value from the left and the value from the right, so using your left side function and your right side function, they need to be equal when x equals 1. So you set them equal, you plug in that value. If this was saying it was 3, we're going to plug in 3, but here it's a 1, plug in 1, solve for a, and that's your answer.